Hi, everyone. Welcome to our fifth module on real-time processing. This is our last interactive crash course module. And so this module kind of serves two purposes. One is to cover what real-time processing is and some of the fundamental concepts surrounding real-time processing. And two is to sort of tie everything we've learned together. So starting with Eeg data analysis, artifact rejection, signal processing like filtering, and then machine learning, tying all of that into how that fits into a BCI, and then how do we make all of that in real time as well. So to kick us off, here's our kind of outline for what we're going to go over today. We're going to start off with the recap from everything we've covered so far, so all the key components that I just talked about. Then we'll go into kind of conceptually understanding what real-time processing is and why that's kind of necessary for brain-computer interfaces. And then we'll tie that into the overall schematic of end-to-end, how do you go about building a brain-computer interface? So this image you must have seen in our first module. If you haven't gotten and seen that, I urge you to kind of go and check that out and follow everything in order, because it'll just make the most sense that way. So we've seen these images previously, and on the left, we have someone who has an EEG set up on their head. They're wearing a cap, they have the electrodes, and here's what EEG data looks like. So EEG data is, capturing electrical activity from the brain in terms of microvolts per millisecond. And on the right side, you see for every electrode, there's corresponding electrical activity that is being picked up. And to the naked human eye, it's just a bunch of squiggly lines, as electrical activity tends to be. And it is up to us to kind of use this data and interpret this data and process this data in such a way that we can make meaningful insights from what is happening and use that to control a cursor, control a drone, basically map that to executive commands that can be controlled using a brain-computer interface. So the electrodes are typically, attached using gel, and basically they're put in a systemic order called the 10-20 system. And so every name or every letters and number combination that you see here means something and tells us a little bit about which location the electrode is located on. So F, for example, stands for frontal. F3 and F4 are near each other, and odd numbers are on a certain side and even numbers are on a certain side. Similarly, C stands for central, P stands for parietal, which is kind of like on the top and going towards the back of your head. And O stands for occipital, which is where the occipital lobe is, and that is right behind your head, kind of where it connects to the base of your neck and a little bit above that also. So there is some nomenclature to it, but in general, this is what EEG data looks like, and this is kind of how it is collected and what we use to make a brain-computer interface. So once you have your EEG data, there are certain things to look out for, such as artifacts. So if you remember, EEG data is basically electrical activity that is being recorded from your brain. However, it's not directly on your brain, right? Your brain is inside your skull, and the electrical activities basically go through tissue, go through skin, go through skull, and then are recorded on the surface of your scalp. So there's already a little bit of noise that the electrical current has to pass through. But your body in general is also an electrochemical system. Your muscles, when that you move, have electrical signals and have electrical components to them. Any sort of heart or your cardiac muscles, for example, to your heart rate is also electrically driven or has an electrochemical basis. So your entire body is an electrochemical system, not just your brain. And so any other signals that are being elicited from different parts of your body can also be picked up by the EEG data collection system. And so that's why when you're collecting EEG data, it's important to not move extra or engage in any sort of extraneous movements that can give off any noise or any electrical signals that you don't want. So usually when you have someone that is sitting with an EEG cap or EEG data collection system on their head, you instruct them to not, move their body around too much or move around or get up, because those electrical activities will impact the electrical activity we can get from the brain. And because we're already recording in microvolts, they're very sensitive, they're very small, and so we want to minimize that as much as possible. However, certain noise is inevitable. You are going to have it no matter how much you try. Even eye blinks, for that matter, induce artifacts. So the image that you're seeing on the bottom of the screen is actually an example of eye movements. They're lateral eye movements. So if you move your eyes side to side, like left to right, you would kind of see this rectangular trapezoidal pattern in the electrical activity. And so that is something that is very obvious, easy to be picked up by the naked eye, and something to look out for in your data. And so you will have artifacts. And so what the next step is to process them. How do you deal with that? How do you take them out of your data to make sure you have clean data? Well, so one of the most common techniques you can use is filtering. So filtering ties back into the frequency, the transition from time domain to frequency domain. So milliseconds. Now you do the FFT and you convert that into frequencies. Once you have your frequencies, you can basically selectively select certain ranges or take out certain ranges of your frequency. And a filter is what helps you do that. So in this case, what we're seeing here is a Psd plot. A Psd plot is a way to visualize the frequencies that are present in your data set and the power to which, the extent to which each frequency is present. So that would be the power. So over here, you can see that we are applying a filter to this data set, a low pass filter of 30 Hertz. So we have our cutoff here at 30 Hertz, and we allow all the frequencies to exist at their natural power, whatever that might be. After 30 Hertz, we have a gradual cutoff, and then all the frequencies are essentially muted or dampened. And so this Psd plot is indicating that we are filtering out the frequencies at 30 Hertz because that is what fits for whatever we are trying to do at that point. And so filtering is a tool that you can selectively use to choose certain frequencies and take out noise if that might be possible. In the case of eye movements, eye artifacts are typically not at a certain frequency range, but they can be also corrected for or manually rejected using other statistical means such as independent component analysis, which is a video for another day. But so filtering is not the only way of correcting for noise and rejecting artifacts. There are also other means to do so, but filtering is definitely something important that you should know about because it is relevant for signal processing and BCIs in general. So now that you have your filtered data, it's all clean. You are capturing what you want to capture, and these are your features. An important next step is machine learning. So the objective of machine learning in relation to brain-computer interfaces is to classify movements, emotions, or brain states using EEG data or whatever other physiological biosignal that is being used. There are ultimately two types of machine learning. One is unsupervised and one is supervised. Supervised is easier to grasp. Supervised is basically when you give the model labels data. You tell it that, hey, there are 4 categories that we want to distinguish, or there are 4 states, 4 emotions that we want to distinguish. And here is the data for each emotion and what it looks like. Your job is to understand these 4 different categories and find patterns that can differentiate between them, and then use that to look at something new and predict what category it belongs to. Unsupervised is where we tell the model that, hey, we don't know how many categories we want or what exactly we are looking for. But given this data, can you parse them into meaningfully different categories and tell us what you think are the strongest categories or the most discernible categories? So it's oftentimes easier to think about something like this in terms of a question or in terms of like a real world example. So let's say we have weather data. Supervised learning would say, here's the weather data pattern for the past month. I want you to tell me how many days are sunny, or how many days are cloudy, how many days are windy, and how many days are rainy. And so we would give them data that was representative of each category so they would know, so they would have an example of what each one looked like. And we would then ask them to look at unidentified data and tell us what they would see. In unsupervised learning, in the same example, I would basically throw at the model maybe a month's worth of data or 2 months worth of data. And I would tell it to tell me what kinds of weather patterns it noticed. So it might not divide it as sunny, windy, rainy, and cloudy. It might say, chances of hurricane versus no chances of hurricanes. Or it might group sunny and windy and cloudy and rainy in two separate categories. So you'll only end up with two. So that is kind of the difference between unsupervised and supervised learning. Within supervised learning, there are two kinds of categories. One is regression and one is classification. You can think of regression as covering or predicting a continuous variable, and classification would be a categorical variable. So regression could be, regression could be the age of a person, right? It's on a continuous number line, and you could predict 31, you could predict 32, you could predict 55. And so it's a continuous variable. Classification, for example, would be something that is categorical. So like whether you are happy or you're sad, hungry or not hungry. So our brain states often fall under categorical things, categorical buckets per se. In our case, we're trying to classify eye movements or directions like right or left or north or south. Those would be categories as well. Within regression, there are a bunch of simple machine learning models like linear regression, support vector machine, and polynomial regression. You would choose the model depending on your data type and the distribution of your data. So something that follows a linear pattern, which is probably the simplest model you can go with, would be suitable for linear regression. But let's say there isn't a linear relationship, it's more of a polynomial relationship, or there are curves in your graph between the X and the Y variables, you would use polynomial regression over there. Same thing with decision trees, or same thing with the classification category. There are several machine learning models that fit this category. You can have decision trees, you can have support vector classification, you can have logistic regression, and you would choose a model that best fits what you are trying to go with. So decision trees, for example, allow for multi-classification. So you can have 3 categories, or you can have 10 categories, and decision trees will kind of parse them into each one. Logistic regression, on the other hand, is more suitable for binary classification, when you only have 2 options and 2 categories that you want to classify. So hopefully that gives you some intuition into what machine learning kind of is and how it can be broken down, but more importantly, where machine learning comes in when we talk about brain-computer interfaces and neuroengineering in general. So let's get into real-time processing now. Real-time processing is a core component of BCIs because in order for a brain-computer interface to make sense or to really have any sort of like useful function, it needs to be in real time. When you are thinking of something, when you want to, make your wheelchair go in a certain direction, or you're working with a prosthetic limb and you want to execute a certain command, it has to happen in real time. It cannot have a 1-minute lag. It cannot have a 30-second lag. Your brain, you will never use such a device in which it does not function in real time. So up until now, everything that we've worked with so far has been offline. And offline basically means it is not in real time. We work with our data set when we did signal processing in a Jupyter notebook. We were importing a file, we were plotting it, and we were working with the data set in that way. It wasn't coming in real time. So real time adds another layer of complexity to what you're able to do and how you can process a certain amounts of data. So let's look at this visual aid that we have on the slides. Imagine that the line is an EEG stream. So you're wearing a Muse headband or any sort of EEG device. You have electrodes connected to your scalp. You are capturing electrical activity. You are sending that electrical activity over via Bluetooth to your computer. And you're getting a continuous stream of data in real time. So let's say we start at point 1. Within the first second, I am able to see my data as it's coming in. And over time, I keep getting an accumulation of data. However, this will always be my most recent data. It doesn't matter. Sure, I have visibility into the past, but at that given moment, I can only see a certain amount of data that is coming in and as it is coming in. So that is important to understand. Another key thing to understand is that your processing or your brain-computer interface should only work with the most recent and available data. let's say you're at this point 9, at this timestamp at 9 over here, and you're seeing the most recent data. The data available at this time point and going over here is largely irrelevant to what you're working with right now. So you shouldn't use this in your data analysis. It's kind of like 1 second at a time. You just work with what you have and what's recently come in, and then you let that go and you focus on the next one. So that is kind of how real-time processing works. So you're getting a continuous stream of data, but one thing that you cannot do is pass in a continuous chunk, a continuous long segment of data into some sort of filter or into a machine learning model. It has to be broken up into discrete segments. So the way we do that is we create epochs from the original stream of data. An epoch is nothing but a discrete segment of data. In this case, we broke up our data into 1 second long segments. 1 second is an arbitrary number, but it's a safe place to start, and you can tweak it later on depending on what exactly you're looking for or the speed accuracy trade-off that you are comfortable with. But we initially started off with a 1 second epoch length. And so now from 1 to 2 seconds is one epoch, 2 to 3 is another, so on and so forth. However, there's also another problem within this. Let's say, once again, right, you are at time 9. That is where you are in terms of real time. This is data from 1 through 9 is all in hindsight, which you've used later on, but you have no use for it right now. You are only working with the data that is incoming. So you have to wait 1 full second until you have a full epoch to go, and then another second as more data comes in. So effectively, you're only able to analyze a data once every second, and you're only able to produce output once every second. So your BCI is basically refreshing at a rate of once every second. That, in fact, is not actually that fast. If you think about constant movements like, operating a wheelchair or using a prosthetic limb, you want to, if you're trying to grab a water bottle or some sort of object, you don't want to wait 1 second for the grasp to occur or your mental command to execute whatever it is you're trying to do. 1 second is simply too much of a lag time for something to be useful in a real-time scenario. So here's a solution to that. You keep the epoch length as 1 second because that is probably the minimum amount of information you need in order to decide what to do or to base a command off of. But you overlap the epochs with each other. So we have one epoch starting from 1 to 2. You have another epoch, still 1 second long, but it starts from 1.5 and goes to 2.5, so on and so forth. So you still have these 1 second long epochs, but you overlap them with each other to establish a semblance of continuity. Now, for each epoch that you will have an output, a classification from the machine learning model. So let's say you are collecting your EEG data and you're trying to operate a prosthetic limb. It'll update every 0.5 seconds now because the overlap is half a second. And so you will have effectively 2 commands or 2 updates from your BCI for every second of operation that you do. And that will be far more real time than the 1 second we saw previously. Of course, you can overlap this even more. You can have a 0.8 second overlap, and then subsequently you will refresh your BCI every 0.2 seconds, which might seem almost instantaneous at that point. So it's a trade-off between how much you want to overlap and how much accuracy and continuity you want the user to feel when they're using the BCI, and how much processing power you have in real time as well. So these are things to consider when you're designing your BCI in real time. And I understand that this kind of concept is not the most intuitive to grasp. So hopefully I'm explaining it well, and feel free to rewatch the video. But I think concepts like these make a lot more sense when you're actually building the BCI and coding it, and so you'll get a better understanding of how to design it like that. So let's kind of tie everything back together that we've already learned. So starting off in this first row, we have real-time process, or not real-time, but we have offline processing. You start off with your electrode placement. You prepped your subject. You put the gel on the electrodes, you place the electrodes where you want them to be placed, and you collect EEG data. You then capture EEG training data. In order for the BCI to work, and for supervised learning, which is what we use for this BCI, you need to provide training data. You need to provide the model with data for each category that you're willing or that you're intending to classify. For example, if I'm trying to classify eye movements, up, down eye movements, so vertical eye movements, and horizontal eye movements, I will need to tell the user to move their eyes up and down for, let's say, 30 seconds. And I will also need to tell the user to move their eyes side to side for 30 seconds. These two 30-second long segments of data will serve as my training data. Now I have basically a 30-second long segment of data. I need to process that data. My first step is to divide it into epochs. I divide it into epochs of 1 second long each, and then I do signal processing on that. I do artifact rejection, I remove eye blinks, I filter the data to whatever I'm trying to filter it, and the data is processed. The next step is to train and test the model. So I call a machine learning algorithm to differentiate the patterns between the EEG activity between the two conditions. I want to notice, my eyes cannot notice the difference in EEG patterns, but I want the machine learning model to differentiate between when I'm moving my eyes up and down and when I'm moving my eyes left and right. Here's a visual of a support vector machine that is drawing a hyperplane between two categories. You can see it just separates the blue from the red. And although there are some blues in the red over here, largely the blue has been separated from the red. And that is exactly what we want the machine learning model to do. Now let's tie this in with real-time processing. We have trained our BCI, we have the model, now we want it to work in real time. So as data is coming in real time, I'm streaming the EEG data and I extract singular epochs from the data that is coming in. For each epoch of data, I apply the same processing technique as I did to the training data. We want to stay consistent. We want to process the data in the same way so that it'll be as similar to the training data when the machine learning model looks at it. So after we have extracted a singular epoch, we apply the data processing procedures and we classify it based on the existing model that we trained over here. And that is effectively how the BCI works. Hopefully from this schematic, you can tell that for each epoch you provide, you will essentially be given an output command. And that is why when you overlap the epochs, you are able to generate more outputs per second, which makes it seem as if the BCI is operating in real time. It is not truly in real time in the sense that it is not giving you an update every millisecond or so, but with the refresh rate of maybe 0.1 every 0.1 seconds or every 0.2 seconds, it is close enough to where it is responsive to your brain in real time. And as a user, you feel like you have complete control over the brain-computer interface and it is doing what you want it to do when you want to do it. So this is a key component in establishing real-time continuity. And I hope that makes a lot of sense when you're kind of putting all these pieces together. As usual, thank you so much. I hope this course was really informational and valuable to you. Our main goal is to provide value to people and to make it as easily accessible for people who don't have a background in things like neuroscience, signal processing, and machine learning. If you have any questions, please do email us with any questions about the content. We'll try our best to help you out, and follow us on Instagram and Facebook. Thanks so much.